Hi guys, this is AS Chemistry, Organic Chemistry, and we're looking at organic synthesis. Question 1. A reaction sequence based on propane 1-ol is shown. So we have propane 1-ol here in the center. In reaction 1, it is converted into a carboxylic acid. That means it undergoes oxidation. In reaction 2, it is converted into an aldehyde, also undergoing oxidation. Aldehyde in reaction 5 is converted into a cyanohydrin. So this is nucleophilic addition. Going back to propanol, it is converted into an alkene in reaction 3, which is dehydration, and it is converted into a bromopropane molecule, which is nucleophilic substitution. So reactions 1 and 2 can both be carried out using the same reagents. Yes, because both are oxidation. Identify suitable reagents for reaction 1 and 2. So the suitable reagents are acidified K2Cr2O7. Now, we could have selected acidified KMnO4, but K2Cr2O7 being a milder oxidizing agent is more likely to produce the aldehyde than KMnO4, which is a harsh oxidizing agent and will quickly oxidize the alcohol into the carboxylic acid without giving enough time for the aldehyde to escape if the aldehyde is required. State and explain how the reaction should be carried out to ensure that reaction 2 rather than reaction 1 occurs. So, in order to carry out reaction 2 rather than reaction 1, we should distill the contents so that the aldehyde can escape further oxidation. If we use reflux conditions, the aldehyde produced would be oxidized to the carboxylic acid. So we need to perform distillation so that we can collect the aldehyde in the form of a liquid when its vapor evaporates from the reacting vessel. Identify the necessary reagents and conditions for the reaction 3 and 4. So reaction 3 is conversion of propane 1-ol into an alkene. So that means dehydration is taking place. So we can either have Al2O3 at 350 degrees Celsius carrying out the dehydration, or we could have concentrated H2SO4 at 170 to 180 degrees Celsius carrying out the dehydration. And reaction 4 is conversion of propane 1-ol to 1-bromopropane. So that is nucleophilic substitution. So nucleophilic substitution can take place when we have the reaction of an alcohol with either NaBr or KBr, potassium bromide or sodium bromide, along with an acid. This would produce the bromoalkane. Or another condition is possible if we have the alcohol reacting with either PBr3 plus heat, or we have the alcohol reacting with bromine. In either of these conditions, we can have, in fact, alcohol will not react with bromine directly. we can have alcohol reacting with PBr3 and heat. So these are the two conditions for the production of the bromopropane molecule from propane 1-ol. Complete the reaction mechanism for reaction 5. Include all relevant lone pairs, curly arrows, charges, and partial charges. So this is nucleophilic addition. So we have presence of partial negative and partial positive charges on the C double bond O group. We have presence of a lone pair of electrons on the carbon atom in Cn. This lone pair of electrons gets attracted towards the positively charged carbonyl carbon, which results in breaking of the CO pi bond, and this produces the intermediate with the carbon atom bonded to a single oxygen atom having a negative charge on it. The other parts of the molecule includes a CN molecule, a hydrogen atom, and a CH2 along with the CH3 groups attached to the central carbon atom or the carbonyl carbon atom. So this is the intermediate that is formed, and this intermediate, when it has an H positive ion present in the solution, the lone pair of electrons on oxygen will be attracted towards the electron deficient species, and we will have the formation of the cyanohydrin. So this is how the mechanism for nucleophilic addition occurs on this aldehyde. The product of reaction 5 exhibits stereoisomerism. Draw the two stereoisomers in the conventional way. So the conventional way is to have a central carbon atom with two solid lines, a wedge, and a dotted line forming the fourth bond. So now we will place an OH group on one of the bonds, a CN group on another bond, the hydrogen atom on the third bond, and the CH2 CH3 group on the fourth bond. And in this way, we have formed two stereoisomers of the product of reaction 5. Suggest why a mixture of two stereoisomers is formed by reaction 5. The nucleophile, which is the Cn negative ion, can attack the carbonyl carbon atom from any side. And since the mechanism is not specific for any optical isomer, both isomers are formed in equal quantities. Question 2. A series of reactions starting from 1-bromobutane is shown. So 1-bromobutane reacts with HCN and KCN to produce P, which produces a carboxylic acid. So P is a nitrile. On reaction with NaOH, it produces R, which would be butane 1-ol. And on reaction 2, it produces but-1-ene, which would be dehydrohalogenation, and but-1-ene produces a polymer, polybutene. So draw the displaced formula of the compound P. Compound P is 1-bromobutane. So on the first position, the Br is replaced by Cn. So CH2, and it says displayed, so we'll have to make all the bonds. So CH2 will be rewritten as C single bond H, C single bond H. Then we have another CH2. Then we have another CH2. And then we have another CH2. And in order to complete the chain, this CH2 will be bonded by another hydrogen, making it into a CH3 molecule. So this is the displayed formula for compound P. Identify the reagents and conditions for reactions 1 and 2. Reaction 1 is the acid hydrolysis of the nitrile to produce the carboxylic acid. So the reagents and conditions are HCl plus H2O plus heat under reflux. And reaction 2 is dehydration. So dehydration would require, actually it is not dehydration, it is dehydrohalogenation. So dehydrohalogenation would require NaOH plus ethanol plus heat under reflux. So that would remove one hydrogen and one halogen atom, producing an alkene. And draw the structure of the repeat unit of polymer Q. So polymer Q would be carbon, single bond carbon. This would be the carbon atoms where the double bond was present. On one of the carbon atoms, we would have a CH2 bonded to a CH3, completing the 4 carbon chain. And on the 3 other positions, we would have a hydrogen atom each placed in a square bracket, forming one repeat unit of polybutene. Complete the reaction scheme to show the mechanism of the reaction of 1-bromobutane with NaOH to produce R. So we have the production of an alcohol from a halogenoalkane. So here we have a primary halogenoalkane. A primary halogenoalkane would undergo the SN2 reaction mechanism. So here what would happen is that there is a partial negative charge on the bromine atom, a partial positive charge on the carbon atom, and a lone pair of electrons on the OH group. The lone pair of electrons on the OH attacks the carbon atom with a partial positive charge on it, which results in breaking of the carbon halogen bond. This would result in the OH group replacing the Br atom on the halogenoalkane, producing an alcohol. So the OH group binds from the other end. In fact, we can also show an intermediate in which the bond between the OH and the carbon atom is incomplete, and the bond between the carbon and the bromine atom breaking is also incomplete. So we have two hydrogen atoms attached to this carbon atom and an R group, which is CH2, CH2, and CH3. This is the intermediate. And once the bond forming and bond breaking is complete, the OH bond is now completely, the OH group is now completely bonded to the carbon atom to which the Br was attached. The hydrogen atoms are present, and CH2, CH2, and CH3 groups are present as the alkyl group. So this is the product that is formed, and the mechanism shows the lone pair of electrons on the OH group attacking the carbon atom with the positive charge on it, leading to breaking of the carbon bromine bond. So this is the SN2 reaction mechanism with which an alcohol forms from a primary halogenoalkane. But1-ene reacts with steam as shown to form a mixture of two structural isomers S and T. S is the major product and T is the minor product. S can be oxidized with acidified potassium dichromate to form compound U. S and U both react with alkaline aqueous iodine. So S and U both contain either a methyl ketone group or they contain a CH3 group next to a carbon atom with an OH group present on it. Identify the type of reaction that occurs when but1-ene reacts with steam. So this reaction is called electrophilic addition. The OH group adds on to one of the carbon atoms present in a double bond, and the hydrogen from steam adds on to the other carbon atom present in the double bond. State what can be deduced about the structure of S from its reaction with alkaline aqueous iodine. So it has got a CH3 group next to a carbon with an oxygen on it or an OH group present on it. So this group is present on the molecule of S, is present in a molecule of S. So this part must be present because it reacts with aqueous alkaline iodine. Explain why S is the major product of the reaction of but1-ene with steam. So when S forms, it contains a secondary alcohol. So secondary alcohol formed due to the formation of a secondary carbocation. So a secondary carbocation is more stable than a primary carbocation due to the positive inductive effect of the two alkyl groups present. Thus, formation of a secondary alcohol is preferred over the formation of a primary alcohol. So since the number of R groups are more, they stabilize the carbocation to a greater extent. So its formation would be preferred because when the carbocation forms, it needs to be stable in order for it to undergo a nucleophilic substitution reaction and replace the positive charge on it with the nucleophile. So, but this is but1-ene reacting with steam. Here we would have a carbocation attracting the OH negative ion. This is not nucleophilic substitution, this is electrophilic addition. So here the intermediate would be a carbocation and a nucleophile. The nucleophile would be attracted towards the carbocation, and the carbocation needs to be present, has to be stable. So a secondary carbocation having two R groups or two alkyl groups would be more stable, therefore its formation would be preferred. Draw the skeletal formula of S, T, and U. So S is a secondary alcohol having four carbon atoms, so that would be called butane 2-ol. So that would be four carbon atoms with an OH group present on the second carbon atom. T would be a primary alcohol, so butane 1-ol. So this would be four carbon atoms with an OH group present on the first carbon atom, and U is formed due to oxidation of S, and a secondary alcohol is oxidized to a ketone. And this reacts with aqueous alkaline iodine as stated in the question above. So this has got a methyl ketone group which is visible in the structure drawn in the box labeled U. Write an equation to represent the oxidation of S to U by acidified potassium dichromate. You should use square brackets O to represent the oxidizing agent. So the reactant would be CH3, CHOH, CH2, CH3 upon oxidation with acidified K2Cr2O7. We end up with a ketone which would be CH3, CO, CH2, CH3, and we would have production of a molecule of water. So this is the equation to represent the oxidation of compound S into compound U. Question 3. Some reactions are shown based on methyl propane all. So methyl propane all is a tertiary halogenoalkane. So in reaction 1, it is converted into a tertiary alcohol. In reaction 2, the tertiary alcohol is converted back into the tertiary halogenoalkane. In reaction 3, the tertiary alcohol is dehydrated into a ketone. And in reaction 4, the ketone has, oh, not the ketone, alkene, not ketone. It is dehydrated into an alkene, and the alkene in reaction 4 is converted into two different bromoalkanes. One is a tertiary bromoalkane, the other is a primary bromoalkane. So for each of the reactions, state the reagents, the particular conditions required, if any, and the type of reaction. For the type of reaction, choose from the list. For each type, it may be used once, more than once, or not at all. Each reaction may be described by one or more than one type. So hydrolysis, dehydration, substitution, oxidation, addition, and condensation. So reaction 1 and reaction 2 are both substitution. Reaction 3 is dehydration, and reaction 4 is addition. So reaction 1 is conversion of an alcohol into a halogenoalkane. So for this, we would be needing either HBr to carry out this reaction, or we would be needing NABr or KBr plus H2SO4 to carry out this reaction. And this reaction is known as, according to the names given, substitution. For reaction 2, which is the conversion of the halogenoalkane into an alcohol, we would be needing NaOH aqueous to carry out this reaction, and this reaction is also called substitution. Nucleophilic substitution to be more accurate. For reaction 3, it is the removal of a water molecule. So the reaction will be called dehydration, and the product formed is an alkene, which was mistakenly called a ketone earlier. So it is an alkene that is formed, and dehydration requires either Al2O3 at 350 degrees Celsius to be present, or we could have the presence of concentrated H2SO4 at 170 to 180 degrees Celsius. Both these conditions will carry out dehydration of an alcohol to produce an alkene. For reaction 4, it is the conversion of an alkene into a halogenoalkane. So we have presence of HBr, and it should be present in ethanol, and this is the addition reaction of alkenes, or electrophilic addition reaction to be more specific. This is an addition reaction. So ethanolic HBr is required to carry out this addition. We can actually have just HBr reacting with the alkene as well. And the two products formed would be the one having a Br group added to the carbon atom, which forms a tertiary halide, or to the primary position, which forms a primary halide. So the tertiary would be the major product, the primary would be the minor product in this case. Draw a diagram to show the SN1 mechanism of reaction 2. So this will be carried out in two steps. In step 1, we will have the tertiary halogenoalkane having 3 CH3 groups undergoing heterolytic fission. Because the Br has a partial negative charge and carbon has a partial positive charge, this bond would break, resulting in the formation of a tertiary carbocation. So this would be CH3 bonded to carbon, which is bonded to two other CH3 groups with a positive charge on it. This is the tertiary carbocation that is formed, and we would have a Br negative nucleophile removed. In step 2, the carbocation that was produced will be attacked by an OH nucleophile present in the same reaction mixture. The lone pair of electrons on oxygen will be attacking the positively charged carbocation, which would result in the formation of a tertiary alcohol. And this is how the SN1 reaction mechanism producing the alcohol from the halogenoalkane occurs. 1-bromobutane is a structural isomer of the product of reaction 1. Define the term structural isomer and name the three different types of structural isomerism. So a structural isomer is a molecule, are molecules rather, structural isomer definition. These are molecules, or rather we can say these are different molecules. So we'll make the definition more specific. These are different molecules having the same molecular formula with the same number of atoms arranged in different structural arrangements. So the number of atoms in the molecule remain the same, but they are arranged in different ways in order to form structural isomers. Types of structural isomerism. The first one would be called chain isomerism, the other one would be called positional isomerism, and the third type of structural isomer are functional isomerism. So these are the three different types of structural isomerisms. Next, 1-bromobutane is treated with the same reagents as in reaction 2. Butane 1-ol is formed. Identify the mechanism of this reaction. Explain why this reaction proceeds via a different mechanism from that of reaction 2. So 1-bromobutane contains a carbocation that is a primary carbocation. So this is a primary halogenoalkane. So a primary halogenoalkane undergoes the SN2 reaction mechanism, SN2, which is also nucleophilic substitution. But in this nucleophilic substitution, the carbocation does not form. In fact, we have formation of an intermediate and then formation of the alcohol from that intermediate. So the explanation is the halogenoalkane consists of a primary carbocation which is not stable due to the presence of a single alkyl group. So there is very less positive inductive effect. Hence, instead of a carbocation, an intermediate is formed which is converted into a primary alcohol without the need of forming an unstable primary carbocation. So, because the carbocation is unstable, as it only has a single alkyl group, so the positive inductive effect is very less. So, it is not formed at all. Instead, an intermediate is formed, and the intermediate is directly converted into the alcohol without even the presence of the carbocation, even for a fraction of a second. So, this is what the SN2 mechanism is. The product of reaction 3, methyl propene, does not show stereoisomerism. Give two reasons why methyl propene does not show stereoisomerism. So methyl propene is basically C double bond C and then CH3. So two CH3s and two hydrogen. So it does not show stereoisomerism. So the reason it does not show stereoisomerism is that it does not have a chiral carbon atom present to show optical isomerism, and the double bond present has both the carbon atoms with two identical groups present on each of them. So in this way, due to lack of a chiral carbon atom being present, it will not show optical isomerism, and due to a double bond being present without the identical group on both of them, in fact, both the groups are identical on the same carbon atom, so it will not show geometric or cis-trans isomerism as well. So no stereoisomerism for methyl propene. Next, methylpropene can be polymerized to form polyalkene. State the type of polymerization and draw the repeat unit of the polymer formed from methylpropene. So, type of polymerization would be addition polymerization, and the repeat unit would have a carbon atom with two hydrogen atoms bonded to it, and another carbon atom with two methyl groups bonded to it. So, this is one repeat unit of methyl propene. State the difficulty associated with the disposal of polyalkenes. So polyalkenes are non-biodegradable because they do not contain any esteramide bonds, and they form harmful combustion products. So cannot be burnt as well. Name the two products of reaction 4. So we've got a carbon atom with three methyl groups on it and a bromine atom. So let's draw it. We have a carbon with a bromine and three CH3 groups. So this will be called 1, 2, 3. So the name would be 2 bromo 2 methyl propane. That is the first product of reaction 4. And the second product of reaction 4 would be, it is a straight chain compound with two methyl groups present, CH3, CH, CH3, CH2, Br. So the numbering would start from the Br carbon. So it would be 1, 2, and 3. So this will be called 1 bromo 2 methyl and propane. So the name of the first product is 2 bromo 2 methyl propane, and the name of the second one is 1 bromo 2 methyl propane. The first compound being a tertiary halogenoalkane and the second compound being a primary halogenoalkane. The first one being the major product and the second one being the minor product of reaction 4.